Order! Order! You are an incorrigible delinquent at times. Behave yourself, man!
Now, on the 14th of September last year, the shockwave from one of the most violent events in the universe tore right through the Earth. You didn't feel it? Well, that's because it came in the form of a gravitational wave, a phenomenon predicted by Einstein and today proven and confirmed by scientists in the US after about a century of looking for it. This first detection of a ripple in space-time is a very big deal. As one scientist put it, physics will never be the same again. It also opens up new ways of probing the very origins of, well, just about everything. Our science editor, Tom Clark, now explains.
We have detected gravitational waves. We did it.
They've eluded science for a century, but today, confirmation that physicists have finally caught one of Einstein's gravitational waves.
As they orbit, the black holes are getting closer and closer to one another. The orbit is...
This, they are convinced, is what caused it, a binary black hole collapsing into one. This computer simulation based on the signal they detected. An event so unimaginably violent, it set a wave travelling 1.3 billion years through space-time all the way to Earth.
400 years ago, Galileo turned a telescope to the sky and opened the era of modern observational astronomy. I think we're doing something equally important here today. I think we're opening a window on the universe, the window of gravitational wave astronomy.
It took twin detectors called LIGO on opposite sides of North America to make the discovery. The effect a gravity wave has on ordinary matter here on Earth is very, very weak. The signal the scientists say they detected is believed to have come from two vast black holes, which spiraled around each other before finally crashing together. According to Einstein, the energy this collision released has travelled as a ripple through space, and it's that which LIGO detected. And they did it by firing laser beams down 4-kilometre-long tunnels. The waves caused minuscule changes in the length of the tunnel, less than 1,000th of the diameter of the nucleus of an atom, and it was that which LIGO detected. So how do you even begin to build a machine to measure a disturbance in the force this subtle? Well, get on the train to Birmingham. Physicists here at the university helped build the LIGO detector and are co-authors of today's announcement. To help us mortals get to grips with the discovery, they've made a scale model of the machine. So I can, just by putting my finger on here, it's measuring that change.
That's right.
How much more sensitive is the LIGO instrument than this?
Unimaginably more sensitive. It is actually 14 orders of magnitude more sensitive than this. It's a number that's difficult to imagine. Okay. But when we take this instrument and we scale it up to the size of LIGO with 4-kilometre-long arms, it is capable of measuring the distance from the Earth to the Sun with an accuracy of better than a single atom.
Heavens.
And if I'll be the agency that moves the universe here, and you'll notice an interesting
Back in Washington, one of the greatest minds in physics, now tipped for a Nobel Prize, tried all sorts of ways to explain the basics to journalists. Does this usher in the era of hover boots? Not quite. Time travel? Different physics. But knowing we can detect faint ripples in space-time means scientists can now study the universe in ways they'd only imagined. Observe parts of it obscured by dust, see neutron stars collapse and form black holes, even listen in for the first time on the echoes of the Big Bang itself.
Explaining physics to journalists, a pretty thankless task.
I've been getting away with it all